Okay, good morning, everyone. Welcome back. Please, I hope you're all doing great. So, can you hear me? Is it okay? You can hear me, right? Okay, cool. So, I already posted like the exam solutions and stuff, right? So please take your time and go through. If you find any issues with the grading, I'll be more than willing to correct it, right? So if you find that I deducted some points which are unfair or anything, just send me an email. I'll check it out and then I'll give you back your points, right? Okay. On Wednesday, let me check the schedule. Right? On Wednesday is, let me confirm. This Wednesday is reading day, right? Is reading day, another reading day. So you're not it's not a must for you to attend. I mean, you can choose to attend if you want, but I'll be making a video, right, on that day. And for that video, you have to watch it. It's part of what you need to learn for the latter part, right? So it's going to be, what I'm going to post will be binding. You have to watch it, right? But then as to whether you want to join me or not, that's up to you. You can decide not to come, that's fine. But I'll be recording it at the same class time. So I'll come online like I always used to, right? The same time, 11 o'clock. I'll come here. If there's no one here, I'll just do it by myself. If there's someone here, maybe I'll let you also participate or something. Yeah, but I'll leave a recording on Wednesday, but it's not an official class day, right? Okay, so that's the statement on that. Please, do you have any questions for me on the exam, anything? Okay, and don't forget that the final replaces what? One of your lowest midterm scores, right? So right now, it's all up to the final lap. Like this is the final lap, right? So please feel free to reach out if you don't understand anything. The final exam is going to be comprehensive, but at least I'll give you a study guide, which will kind of like give you an idea of what to expect because you've learned a lot of stuff this semester, right? Okay, so if there are no questions, then let's get on to work. I'm sharing my screen, my desktop. Please, if you can't see, do let me know. Let me make this. Yeah. Okay, so the last time we only had this example to deal with, right? Example 6. That was the only remaining example, and it was an application question under the antiderivatives, right? For rectilinear motion. So last week I told you that when you have we learned in the previous chapters that when you have a position function, then you can differentiate it to get a velocity function. And then you can also differentiate the velocity function to get an acceleration function. Well, because antiderivatives, you can just reverse differentiation. Then that means this time around, when you're given acceleration, you can just go back and get the velocity function by getting the antiderivative. When you have the velocity function, you can just reverse it by getting the antiderivative of the velocity function to get to the position function, right? So the relation is that you can move from acceleration to velocity by taking antiderivative of the acceleration. And you can also move from velocity to position function. So we are going to illustrate this using this example. Now, once more, just as we had initial conditions for the previous case, where the initial conditions allows us to solve for a specific arbitrary constant so that the function is specific instead of a family of functions. We can also be given initial conditions under the position for the position function or the velocity function so that we solve for a specific arbitrary constant value so that we get a specific velocity function or position function, right? So initial conditions apply here too. So let's look at this example. So a particle moves in a straight line and has acceleration given by a of t equals to 6t plus 4. Its initial velocity is v of 0 equal to negative 6 centimeters per second. And its initial displacement is s of 0, which is 9 centimeters. Find its position function s of t, right? So in this problem, we are given the acceleration and we are asked to go back to the position function, right? So let's solve that on the whiteboard. I'm sharing the whiteboard now. If you can't see, do let me know. Okay, so example 6 on slides, we have a of t. The acceleration function is given by 6t plus 4, right? And you're given some initial conditions. The total as v of 0 is negative 6 centimeters per second. And then the position at 0 is also 9 centimeters, right? And find s of t. Okay, so let's do this. Now to get to s of t, we need to get the antiderivatives, right? So for a of t equal to 6t plus 4. When we get the first antiderivative of the acceleration function, that will give us the what? The velocity function, right? So that'll just be finding the antiderivative of this. So that'll be 6 t1 plus 1 over 1 plus 1 plus 4t, and then plus what? An arbitrary constant c. Now you can simplify this a bit, and you get 3. It is 2. 2 goes here, 3. 3t squared plus 4t plus c. Now, we are given an initial condition for the velocity. So because we're given an initial condition for the velocity right here, we can what? Try using this initial condition to see if you can solve for one of the arbitrary constant. Well, there's only one here. It's just c. So we can solve for c here, right? So v of 0 equal to -6. So that means that 3 times what? When you plug 0 for t, so that'll be 3 times 0 squared plus 4 times 0 plus c. That will give us -6. Right, so this setup will give us an equation that we can solve for the c. So we have -6 equal to 3 times 0 is 3 times 0 squared is 0, 0, right? 4 times 0 is 0. So we just have c equal to -6. That means that a specific velocity function is given by what? 3t squared plus 4t, and then c is we have -6. But then it's not the velocity function we're asked to find. We're asked to find a position function. So we know that the position function is just the antiderivative of the velocity function. So we proceed to get the position function by getting the antiderivative. So that will be 3t2 plus 1 over 2 plus 1 plus 4t1 plus 1 over 1 plus 1. And then minus, for the constant, you just slap the variable on top, right? So just multiply the variable by it. So 60, and then plus. Well, here you can choose to bring the same c, but because I already brought c here, I don't want to like mix it up, right? I don't want to get it mixed up. So I'll use a different arbitrary constant d to denote the second level, right? Okay, so now I'm finally here. Let me simplify this a bit. I have the position function s of t. This 2 plus 1, 3. It cancels out. We have 3 t cubed, and then this 2 and 2. So that'll be 2t squared, and then this -6t, and then plus t. Now, when I'm here, right, you notice that I'm also giving an initial condition for the position function. S of 0 is equal to what? 9. So with that, I can use this to solve for what? So that's 0 cubed. I can use this to solve for the arbitrary constant d. So that's 0 cubed plus 2 times 0 squared minus 6 times 0 plus t, right? And that should be equal to what? 9. Now, all the zeros cancel out, so that leaves us with d equal to 9. So we finally have our position function, which is a specific function form, not a family of functions, because the arbitrary constants have been solved for, right? So plus 9, and that's it. This is our position function. Please, any questions here? Okay. So that's all on this one. Anybody needs like extra time here, a lot of time here to take notes? Okay, then that's it for this section. I'm going to switch. Okay, so let me just run through these so that you know we have an end. So we have the solution here. Get the velocity function, use the initial condition to obtain the arbitrary constant and the velocity function, get a position function, and then use the initial condition to get the arbitrary constant and the position function. Then that'll give us the position function, the exact position function. And that's all. Okay, so then let me move on. Let's move on to the next one for Appendix E. Appendix E. Now, for Appendix E, right? This is just an introduction to the chapter 5, something that we need to know. No introduction necessarily for chapter 5, but something we need to know going into chapter 5. Right, so that's Appendix E. I'm sharing the PowerPoint for Appendix E. Please, if you can't see, do let me know. Okay, so now for this one, Appendix E, we are going to introduce something we call a sigma notation, right? So a sigma notation is just a convenient way of writing sums. Now we use this Greek letter sigma, right? Capital sigma, right? it corresponds to the letter S, and it's called a sigma notation. Kind of like the reason why they use S is, I guess, is sum, right? Sum, way of writing sum, so sigma, right? Okay, so that's capital sum. Now, with this notation, let's see how the structure is like. Now, suppose I want to add some like a sequence of numbers, right? So say a sub m plus 1, and so on up to a sub n. Now, suppose these are real numbers, right? Now, instead of writing their sum as a sub n plus 1 plus a sub n plus 2 plus and so on, this long thing, instead of writing this long thing, right? Instead of writing this long thing, well, I can kind of like write it using the sigma notation into a much more compressed and convenient form. Oh, I see something in the chat. Oh, wait. Okay, Megan. Wait, Megan, where did you need? I just saw your chat. Where did you need help? Did you?
Oh, it's okay. I just needed it for slides, but I'm okay now. Thank you.
Okay. I just saw that. Okay. Whenever this happens and it's an emergency, you can just speak. I'll then see. I'll then stop right away and let you see. Yeah. Okay. So back to what I was saying. So instead of writing this long thing, right? A sub n plus 1 plus and so on and so forth, we say, okay, let's get a notation that we can use to compress this, right? So that's where sigma notation comes in. So with the sigma notation, what you're going to do is, you see for this one, we have an index for the sequence that we have here, right? This n plus 1 and going on up to n, right? So the index for the numbers are n plus 1 and so on up to n. So the commonality between the numbers is just their indexes, right? That's what we use to note where they are, like what the specific number is. So what we can do here is, you can just write a sigma notation. You can write the sigma symbol like so. And then you say, okay, now let me generalize the index as I, right? And then for the I here, the I is going to start from M and is going to end at N, right? So this is where we end, and this is where we start from. And then the I is just used to indicate which kind of number we are dealing with, whether it's a sub n plus 1, or a sub n, right? So I just attach the I here. Now, in attaching the I here, if I just have this symbol, then I have I here. All that I'm doing is, with this sigma notation, right? This is a sigma notation. What I have to do is just come here, look at what is underneath the sigma symbol, right? It's I, right? This I here will tell us where, for what is in front of the sigma, you have to start plugging in this number and then end with this number, right? And then you sum all of them together. So when I start, I'll say, okay, if this was there without what is on top here, right? Suppose we didn't know this whole line, we didn't know this. And then I just had this sigma notation here. Now I'll say, okay, I have a sub I. Okay, then let me just go down here. Whatever this one is, this I here tells me where I'm supposed to start plugging the I from, right? I'm supposed to start plugging I from M into whatever expression is in front of the sigma, right? And then I'll keep plugging in until I get to N. And the increase is always 1 at a time, right? You don't increase twice or 3 times, right? It's going to be systematic. Like if I is 2, the next one is 3 and 4 and so on and so forth. If I is -1, the next one is 0. So you keep adding 1, the increments is 1, right? So I'll say, okay, I start from M. So wherever I see I in front of the, in the expression in front of the sigma, I'll plug in the M. So I start with A M sub M, because the I is sub M here. Sorry, the I is sub I. And then the next number that I'll have to plug in is what? Is M plus 1, because when I start with M, the next one is M plus 1, the next one is M plus 2, and I'll keep going on and on. And then I know for sure that the last one is N. Now, if the last one is N, can someone tell me what the last but 1 will be? If the last one is N, and you know that the increments are 1, what will be the last but 1 term for the sequence? So M plus 1, M plus 2, that, something, and then N. What is that? Can anyone guess what it will be? What will be the last but 1, right? You know the last one will be N, but what will be the index preceding the N? Can anyone guess? Okay, let me see. Perfect, perfect, perfect. N minus 1, right? Because the increment is always 1. So in order to get to n, the previous one should have been n minus 1, right? N minus 1, right? So with this index, we'll just be plugging this index into the what? Wherever we see the I here. The I is just showing us what we are going to plug the numbers into for the expression in front of the sigma, right? So A sub I, we start with m. The next one will be, we know that from m, we get to m plus 1. So that'll be A sub what? M plus 1. And then the next one will be your m plus 2. So wherever we see I, we plug in m plus 2. So that'll be, let me just separate these. So that'll be A m plus 2. Now you keep going on and on and on, right? And then we write we can do the last but one, which will be A n minus 1, and then plus the last one, which will be A sub n, right? So right from here, I've been able to show you how you can move from sigma notation to write it as a sum, and how you can move from a sum to a sigma notation. Please, any questions so far on this? Anybody needs time on this slide? Okay. Now, we can also write, because this A sub I is just a function of I, we can write it in function notation for the sigma notation, right? This f sub I here is just A sub I, right? It's a function of I, right? So this is just a function notation. So with that one, you still employ the same thing, right? Wherever you see I in the expression in front of the sigma, you plug in the index, right? So we start with m, and you're going to end with n. The increments will be 1, right? So the first one, m, plug it in, right? So that'll be f of m. Plus the next one, m plus 1, plug it in. Wherever you see I, plug in the m plus 1. And that'll give us this 10, f of m plus 1. And so on and so forth, right? Keep going until you get to the last one, right? Now let's look at the parts of, like some of the definitions of the parts of the sigma notation. Now, obviously, this expression, this symbol is a sigma, right? That's the first thing we learned. Now, this I here, which indicates which index we are up to, it's kind of like literal, but it's called an index of summation. It's literal, right? Index of summation. So it tells you which term you are dealing with, right? So if it's m, I know that, oh, it's the first term, and then m plus 1, oh, the next one, and so on and so forth. And then the index tells us where we have to begin from and where we are going to end, right? So the index takes on values from the start to the end, right? So these are more like I from m to I equal to n, but we don't write the I when it's on top, right? We assume that we know that the I will take on the end value here, right? Now for the index of summation, feel free to use any other letters, but usually we don't use a letter which will conflict with either the ending value or the beginning value, right? So we don't do something like, usually we don't do something like I, yeah, it looks weird, like maybe n, and then A sub I, it makes it complicated. So we this has to be different from, the index always has to be different from like the sequence, right? The sequence of numbers, or the sequence of alphabets, right? So that's it for this. Please, any questions on this? Okay. Anybody needs time on this slide? Okay, now let's look at some examples of writing it from sigma notation to a sum. So for the first one, we have sigma I from 1 to 4, I squared. So the expression in front of the sigma is I squared. So we say, okay, let's just go underneath the sigma notation or the sigma symbol, right? And then look at where the index of summation is starting from and where it ends. The index of summation starts from what? 1, right? It starts from 1. I squared, yeah, it starts from 1 and it ends at 4. So you plug in the first term, which is 1. So that'll be 1 replaces I, right? So that'll be 1 squared, right? Plus the next consecutive number, that'll be 1. From 1 you move to 2. So that means I is now taking on the value of 2. You plug it in here, you get 2 squared. The next consecutive number is what? Is 3, right? So I will be 3, right? So 3 squared for the next one. The next one will be 4. But then when you get to 4, keep looking at the top here, right? 4 is the last number, right? So when you get to 4, you do 4 squared, right? The I can take on bigger values than 4. So this is where we are now. And when you do the summation of this, you get 30, right? Now the same for this. We don't always have to start from 1. You can start from, say, 3, right? So for this one too, you just look at the index of summation. Check where it's starting from and where it ends, right? And wherever you see the index of summation in the expression in front of the sigma, you plug the current index in there, right? So we start with 3. So 3 here, right? Wherever you see I, put in 3. So that'll be 3. And then the next consecutive number is 4, right? You plug 4 in I, you get 4. And the next one, 5, and so on, keep going. The last but one is n minus 1, and then the last one is n, right? Please, are you okay so far? Any questions? Okay. Now, as you saw with the function notation formula, the sigma notation, this expression, okay, I see something in the chat. I call this up. How do you get from 5 to n? Okay, so from 5 to n, right? Because the n was not specified, we didn't specify the n as say 10 or something. We just start with the pattern, right? So say 3 and I. So when I is 3, it takes on, we plug it in here and we get 3. When I is 4, we plug it in here. When I is 5, we plug it in there. But we can keep going on and on. The n was not specified. We don't know the exact n. So that's why we do, okay. So maybe we've done a couple. So we say, okay, so plus and then ellipsis and so on. And then plus, and then we do like the last part. So you can do the last part 1 and then the last one, which is n. Please, I hope it makes sense now. No, that won't be equal to infinity because here the n can be specified to be a number. We can specify the n to be a number. Someone could even also say that the n is infinity. You see, so it could be either infinity or a specific number. So you could go to infinity. It's possible, yeah. So it's possible to have, yeah. So when you get to, so it's possible. Let me say possible to have something like this. Let me use the same thing, infinity, and then. So for that one, you just be doing 1 plus 2 plus 3. No, sorry. What did I say? 3 plus 4. We start at 3. So 3 plus 4 plus 5 plus 6 plus blah, blah, blah. So that one you do this, you not n. But then they can also specify the n. Yeah. Okay. So now moving on, let's look at C. Please, I hope you're okay so far. If you have any questions, let me know. And oh, the quiz on Thursday will be based on like sigma notation stuff. Okay, so now let's move on. Now for C, the same principle, right? You look at the function in front of the sigma, right? And wherever you see the index there, just plug the current index value in that function, right? So we start with j equal to 0. So the thing is 2 to the power j. So when j is equal to 0, plug it in the 2 to the power j. That'll be 2 to the 0, right? And then you move on to the next consecutive index. That'll be from 0, you move to 1, right? So when j is 1, you plug it in 2 to the power j. That'll be 2 to the power 1, right? Which is this term. And then the next one is 2, right? When j equal to 2, you do 2 to the power 2. Next, 2 to the power 3, 2 to the power 4. And then the last one is 2 to the power 5. So when we get there, we just stop there, right? And if you're asked to get the sum, you do this math and you get 63, right? Well, it's the same idea for the D2, right? The function here, this time you see they are alternating the index now. We use j and then we're using the k, right? You're not limited to always using I. You can use whatever index. As I said, as long as it doesn't make the notation messy. I say you have some alphabet and M and starting from M, no. That one will make it messy, right? But if apart from that, you can just use any alphabet you want. You can even use Greek letters. You can have like tau from 1 to n, right? It doesn't really matter. It's still the same concept, right? You look at the index of summation, where it's starting from, and then you look at the expression in front of the sigma notation. And then moving through the consecutive numbers of the index of summation, you are just going to plug them in and then keep adding. So with this one, we start with k equal to 1. You plug it here, we have 1 over k. So that'll be 1 over 1, right? And then the next one, k takes on the next consecutive number, which is 2, right? So wherever you see k, you plug in, you plug 2 there. So that'll be 1 over 2. So that's the second one. And then the next consecutive number will be 3, right? So wherever you see k there, you plug in 3, that'll be 1 over 3, right? Plus. And then you keep going, because this one, they didn't specify the n, you keep going until you get to what? The 1 over n, right? And that's it. Well, the expression can even much more nicer, right? Much more interesting. We can have an index of summation which has this, but it's still the same concept. Check the function in front of the sigma, right? And then you'll be plugging the consecutive index of summation values in that expression, then add them all up, right? So with this one, we see this expression, we are starting from 1. So I plug in 1. The first one, wherever I see I plug in 1. So that'll be 1 minus 1 over 1 squared plus 3, right? So that'll give me this first term. And then plus the next consecutive index, that'll be 2, right? So wherever you see I, you plug in 2. So that's 2 squared, right? Minus 1 and 2 squared plus 3. That's the second one. And then for the third one, you have I equal to 3, right? So you plug that also in. But please pay attention to the upper, like the upper limit. That one is 3, right? That's the upper limit for the index. So when you get to 3, we just stop there, right? And then if they ask you to simplify or solve for that value, you can get that to be this. Okay. Another interesting example is when there is the index of summation cannot be seen in front of the sigma. Well, it's still the same idea. Do you remember that if you have something like f of x equal to 2, right? And then we ask you for f of, say, 100. What is that? F of 100 is what? If f of x equals to 2, what is f of 100? Anybody? If f of x equals to 2, what is f of 100? Okay, I have 2. A different answer. I have 2. Well, that is not incorrect. You're right. It's just direct. If a function is constant, it's a constant function, then any s value is still constant. It's a horizontal line. Any s value is still the same thing, right? It's 2, right? F of 100 is 2. F of a billion is 2. F of 10 is 2. F of 0 is 2. Anything, any s that you can think of is still 2. Now, that idea applies here, right? So when you have an index starting from 1 and then ending at 4, you know that you always look at the expression in front of the sigma and then plug in the current index, right? So when we start at 1, if the function is 2 and you plug in 1, right? The function is constant. So when you plug in 1, it's still 2. When you plug the next index, which is 2 in there, it's still 2, right? So you keep going and then you get what? This 2 plus 2 plus 2 plus 2. Please, I hope it makes sense. Right? Don't forget that the expression in front of the sigma is just a function of the index, right? So this like f sub I, f of I equal to 2. That's what this means, right? So no matter the I, it's still going to be 2. Please, are you okay with this? Any questions? Anybody needs time here? Okay, so we've seen some examples of how to write forms. Is someone speaking? A question?
Yeah, I have a question. Like whenever you have a function like this, you mean you put the same 2 up to maybe you n number?
Yes. So you see this one occurs 4 times.
Yeah.
Because there are 4, looking at the index of summation, there will be 4 consecutive numbers that you'll be using. Yeah, so it's essentially doing, if it's a constant, then it's essentially just doing, we will establish that principle later on the next slide. It's just going to be the constant times, so the length of that interval, how many times and how many indexes are there. So you see, this one is just 2 times 4. Yeah, that's a good question. Yeah.
Okay, thank you.
You're welcome. Please, any questions on this? Anybody needs more time here? Okay. Then let's move on. Now, we just saw how to write from a sigma notation to the sum, right? But this time, let's do it. Let's work backwards. This time, we'll be given a sum, and then you have to write it in sigma notation. So with that one, we're looking at example 2 here, right? So we have 2q plus 3q plus and so on, ellipsis, plus nq in sigma notation. Well, the interesting part is when you have the sigma notation, you want to write it as a sum. In most cases, you have to write it in an exact form, right? For each of these examples, you see it's one way. There's only one way to write from sigma notation to the sum. However, if you have the sum, then you are not limited to the number of forms you can write the sigma notation, right? So with this one, if you are given the sum like so, it turns out that we can write it like this in sigma notation and it will work. Because think about it, if you have just this, and then you didn't know this side, and you are trying to write this sum, the first index will be 2. The next consecutive index will be 3. The next one will be 4. And it keeps going. The last one is n, which is the same as what this. So that means that this is a correct sigma notation. On the other hand, someone can say, nah, this is too boring. It's too direct. I want to change my ways. I want to make it more interesting. Well, someone can say, okay, why don't I make it j plus 1 here, like so, right? And then to the power 3, and then start my j from 1, and then n at n minus 1. Well, for this one to just consider only the sigma notation, right? Let's say we are trying to write this as a sum. Well, if you start with the first index, it's 1. So that 1 plus 1 is 2. 2 cubed. Oh, nice. It matches the first one. What about the next one? Well, the next consecutive index is 2, right? 2 plus 1 is 3, right? So you get 3 cubed. Oh, that also fits. Okay. Now, what about the next one? Let's say the next index will be what? Is it 4? No, wait, 3. I did 1, 2, 3. Yeah, so the next one is 3. So that'll be 4, 3 plus 1, which is 4. I'm getting ahead of myself. So that'll be 4 cubed. Oh, it also fits what is going to follow. And then we keep going. The last one will be what? N, so bring your ellipsis. The last one will be n minus 1 plus 1. N minus 1 plus 1 is n. So the last one, you get n cubed. And it matches this exact sum, right? The exact series that we had there, right? And then another example is this, right? Suppose you have k from 0 to n minus 2, k plus 2 all cubed. For this 2, at 0, we get 2 cubed. At 1, we get 3 cubed. At 2, we get 4 cubed. And is they going to be the same thing? The last one, n minus 2, that'll be n minus 2 plus 2, which is n cubed. This is still going to match this series. So when you have the series, you are not limited to the number of ways. In fact, you can even write several other ways. There are several other ways you could have written this. And you can try and figure it out yourself. You can like try some examples out and see if you write a sigma notation, if it will match the structure, right? But there are infinitely many ways you can do it. Please, any questions on this slide? I hope it makes sense. Okay. Anybody needs more time here? So there's an answer that would be correct. Oh yeah, so any of them could be correct. But in your homework, what they usually do is they will, because they know that there are infinitely many ways, they can fix the sigma for you. Let's say, suppose they fix it like this. And then you are, this option is out and that option is out. Their only way to write it is like this. Does it make sense? Yeah, so they can fix the sigma for you and then they ask you to write this. And that's one option they can do. But because it's infinite, they will limit you somehow so that you can use only one. But you have to just know that there are infinitely many ways of doing it. Please, I hope it makes sense. Are you good? Or no? Does it make sense? Okay, cool. Okay, then let's move on. Now, these are some theorems that regards working with sigma notation, right? Let's look at some simple rules for working with sigma notation. Now we're going to look at 3 simple rules. The first one says, when you have a sigma notation in this form, right? So sigma I from m to n, c a sub I. Well, this is equal to what? C and then sigma I from m to n of a sub I. Now, what we notice here is the a sub I is dependent on the index of summation, but the c is a constant. It does not depend on I, right? So all that this is saying is more like the constant multiple rule kind of thing, right? When you have a constant times some function which depends on the index, right? And the constant doesn't depend on the index. You can always factor the constant out of the sigma, right? So you can just move the c out. You have C sigma I from M to N A sub I. Well, a proof to this is, let's do the proof. A, you're proving that sigma I from M to N of A sub I. Why is this equal? Oh, C is here. Why is this equal to that? Okay, so let me start with this. Now, when the I is M, right, I'm plugging it in the function in front of the sigma. So when I is M, I'll get C A sub M plus the next consecutive index is M plus 1. So that'll be C A M plus 1. The next consecutive index is going to be M plus 2. So that'll be C A M plus 2. And I keep going, right? And then the last one will be C. The last one will be N, right? So it will be C A sub N. Well, because the C is a constant and it occurs in each and every term, I can just factor out the C, and then I have A sub N plus A sub N plus 1 plus A sub N plus 2 plus what? And so on plus A sub N. Well, what is this? Well, this one here is just some from, you can use the sigma notation for this. It's just this A sub I. And then there's a C multiplying out here. So you just do C times this. So that's the proof. Right, that's the proof. Okay. So just note that. So let me write an example. So say, let me say some example, a quick example. So suppose you have something like sigma I from say 1 to say 3 of say 4i, I squared. Then you can say, okay, this is a constant. It doesn't depend on I, right? The index. So I can factor out the 4 and then do I from 1 to 3 I squared. That's a good example. Please, I hope you're okay with this. Any questions here? Okay. And I'm going to go back. Now, what about the B? So for the B, we are saying that the when you have sigma I from M to N of a sum, right? So we have A sub I plus B sub I, right? Then it's just going to be what? A sum of the sigmas, the sigma notations, right? I should say sigma notations. So that's just going to be sigma I from M to N of A sub I plus or sigma I from M to N of B sub I, right? Now let's look at this. Let's look at how that looks. That's the proof for that one, right? So I from M to N of A sub I plus B sub I, right? So, okay, so for this one, let's use this entire expression is in front of the sigma. So let's write it out as a sum, right? So the first index is M. So I'll plug in the M. So that'll give me A sub M plus B sub M. The next index will be M plus 1. So I'll plug that in there. So I'll get what? A sub M plus 1 plus B sub M plus 1, right? And then I'll keep going. The last index is what? Is N. So if I plug that in, I'll get what? A sub N plus what? B sub N. But then when I get here, I can see that, I can say, okay, let me group the terms with A, right? So this is going to be the same as doing A sub N plus A sub N plus 1 plus all the other A's in between. And then the last A, which is A sub N. I can do this. And then plus, for this B sub M, I can group all the B sub M's to as a sum. So that's just B sub N plus B sub M plus 1 plus all the other B sub M's, right, in between M plus 1 and N. And then the last one is B sub N. But then when you get here, you notice that this A sub M to A sub N is just the sigma. We have a sigma notation for that one. It's I from M to N of what? A sub I. And then plus for this second piece too, it's just going to be what? I from M to N of what? B sub I. So that's a proof. A preference as to how to write it. I'm not sure how you mean actually. Can you point me to like a step that I'm doing and maybe compare them? Are you talking about which one? Is it the sigma notation or the?
On number B, you have 2 equal signs that you could write it this way or that way, and it still makes like it's.
Oh, okay, okay. So you mean like this step and this step and then that step? You mean this step and that step, the last one, the last but one and the last one?
Yes.
Oh yeah. So I'm not really focusing on how you're going to write it, right? I'm just trying to prove that this one is like this. And I'm proving it by writing it in this form. You see, in this form, in the sum form, in the series form.
I
I'm
got you.
writing from the series to the sigma, yeah, so that I can prove this. Yeah. Okay. So I hope you're okay with that. Any questions on this? Right. So this is a proof that whenever you have a sigma notation of a sum of expressions, you can just do the sum of the sigma notation of each individual expression term. So an example for that one would be this. Let me give you an example. So suppose you have, say, I from, say, 1 to, say, 10 of, say, I squared plus I cubed, right? Now this is a sum here, right? Two terms, right? Because the sigma notation is it's a linear operator, right? That's what we proved here. I can say, okay, now for this one, I'll just do, okay, just do the sigma of the first from 1 to 10 of I squared plus the sigma of the second, right? And that also works. So you can spread it out like so. Please, are you okay with this? Any questions here? Okay. Now the last one I'm not going to prove, it follows from the B, right? The sigma of the difference doesn't look so clear, it looks blurry. Let me put the minus here so that it looks much more pronounced. Yeah, when you have the sigma of a difference, it's just going to be the difference of the sigmas, right? Now this one is from A and B, right? When you look at A and B, if A and B apply, then C also applies. Now, how do I mean? Now, because for the C, let me just do it here. I from M to N, A sub I minus B sub I. Well, that's just the same as I from M to N of, this one is A sub I plus negative B sub I, right? When you have something minus something, the same as plus the negative of that. Now, because it's plus, I know that the sigma of a sum is just the sum of the segments. So I can do this. I'm not going to ask you to prove. That's why I'm kind of like brushing on these proof. But I just want you to understand why all that I'm saying is true, right? So plus this B sub I, like so. But then this B sub I is negative B sub I is the same as -1 times B sub I. And we learned from part A that whenever you have a constant times something that depends on I, you can pull the constant out. So in that case, I can pull out the -1. So that gives me sum M to N A sub I plus and minus, right? So if I pull out the negative, it affects this plus to make it minus, and then sum I from M to N of B sub I. So that's it for the C, right? So it follows from A and B. But I'm not going to ask you to prove any of these. Yeah. Please, any questions on these? Okay. Now, I think this is what Daniel was talking about when he said that for the constant, whenever it's a constant, it's just the constant times how many indexes are there, right? So this is what I was talking about when I said we talk about it in the coming slides. So here we are now. Whenever you have a sigma, right? This one is from I from 1 to N. When you are typing it, sometimes it comes like this. So just be wary of this. When you see this, it's still the same thing, right? So this of 1. Right? So what that means is you're going to sum 1. Wait, or the solution is on this. Oh yeah. So what that means is you're going to sum 1 what? N times, because when I is 1, if you plug 1 in here, you get 1. When I is 2, if you plug 2 here, you still get 1. When I is 3, if you plug it in here, you still get 1. And it keeps going on and on. When I is N2, when you plug it in, you still get 1. But how many terms are there? There are N terms because there are N indexes. So that's the same as doing 1 times what? N. So that's equal to N. Please, I hope it makes sense. Any questions? Okay. Anybody needs time here? Do you know? Okay. So now let's move on. Now, what about if you are summing the first and positive integers, right? So prove the formula for the sum. You're not responsible for this proof. So I'm just going to show you how they do it, but you're not responsible for the proofs, right? So you're not going to spend too much time here on these proofs. So this proof is going to be important though, like the end result, this value. This is going to be important, but the proof in deriving this is not going to be tested. Okay, so now suppose you are looking at this sum, right? The sum of the first and positive integers. That means that I is from 1 to n, and then we have I in front of the sigma, right? So when I is 1, that is 1 here. When I is 2, you have 2. When I is 3, you have 3, right? And then the last one is n, you have n. So this is the sum of the first and positive integers. Well, this one says if you're doing that sum, it's just going to be the same as just do the upper limit here. So you have n plus 1 all over 2, right? So suppose I want to sum the first 10 integers, right? The first 10 integers. Then it's just going to go 10 plus 1 over 2. And that's equal to this 11, 5, 55. I'm done. Now you see, this is very efficient, but it will surprise you that the proof to this was developed by a 10-year-old called Carl Friedrich Gauss, right? He's a German mathematician. He discovered this when he was a 10-year-old. The anecdote goes this way. So they said that they were probably talking in class, right? So the teacher comes in and said, okay, you guys have nothing doing. Oh, I see. So what you guys can do is just sum from, let's say, 1 to 100. So the professor just sits down, so happy that, oh, I gave these kids work. They're probably not going to be done. It's going to occupy them. But then all of a sudden he sees this kid, this 10-year-old kid just walking towards him. It's like, I'm done. He's like, well, how did you do it? So that's like the story behind this. So this 10-year-old proposed this way of finding the solution. So this is how you went about it, right? So suppose you are trying to find, the sum of the first and positive integers, right? So Carl Friedrich Gauss says, okay, so for that one, let S be that sum. Oh, just skipped. So let S be that sum. Now, if S is that sum, then what you're doing is you want what? 1 plus 2 plus 3 plus 4 out to n. And then Carl Friedrich Gauss realized that if you flip this, right, instead of the 1 plus 2 plus 3 up to n, if you flip it into n plus n minus 1, and then plus, you keep decreasing it up to 1, well, they will match because they have the same number of terms, right? So you just flip it, and it's still going to be the same sum, right? So flip it, and you have n minus 1 plus n minus 2 plus, and so on. The last but one will be 2, and then plus 1. Well, the thing is, in writing it in this form, with this simple trick, if you add this side, s plus s, you get 2s. If you add this first term, 1 and n, you get n plus 1. Plus, if you add this next term, 2 plus n minus 1, you get n minus 1, n plus 1 again. If you add the next term, 3 plus n minus 2, that's still n plus 1. So you keep adding, but at each step, you get n plus 1. Right? And then the last one, you still get n plus 1. So how many terms are there? Recall that there are n terms, right? N terms. So that means that this the same thing will occurring n times. So that means that the 2 of the sum is equal to what? N times n plus 1. And then when you get here, it's a matter of solving for the s, which is what you use to denote the sum. So what do? Divide both sides by 2, and you have s equal to n plus 1 over 2. And that's the proof, right? So that's Carl Friedrich Gauss, the 10-year-old who discovered this, and that's how he did it. Yeah. Please, any questions on this? As I said, I'm not going to ask you to prove. I'm just going to run through the proofs to let you get the ideas of how some of these things come about. I'm not going to ask you to prove, but this is it. This is elegant proof. Yeah. Please, any questions here? Okay. Anybody needs time here? Okay. So all that you have to know is this one. The sum of the first n is equal to what? N plus 1 all over 2. That's all. Now, another one, which is an interesting one, is the sum of the square of the first n positive integers, right? So this one is sum of the square. So that's I from 1 to n of I squared. Well, the proof can be done by telescoping sums, but well, if you're interested, you can just let me know. I'll try and show you how that is done, but I'm not going to test you. And it's too much of work and it's not going to be tested and it's going to be too much of work. So we are going to avoid it, right? But the final output that you have to know is what? The sum of the square of the first n positive integers is equal to what? This time is n, let's go back. It's n plus 1 times what? 2n plus 1 all over 6. Right. Now, with that, we have like a full list of things that we have to be wary of. This is where I'll end today, right? So the sum of the first of a constant 1, n times is just n. Whenever it's a c, it's just n times c, right? The sum of the first n positive integers is just n plus 1 all over 2. And the sum of square of the first n positive integer is just n plus 1, 2n plus 1 all over 6. The sum of the cube is just this. So you use this when you get to chapter 5. So I'll say note please. Right. So that will be all for today. It's 11:50. Thank you for your time. I'll continue with this on Wednesday. You can join me if you want to, but you're not bound to come to class. Right. So all the best. If you have any issues on the exam 2, feel free to reach out. Yes, so thank you. Bye. You're welcome, guys.